Okay, Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. In this sixth lecture, we're going to basically finish what's left from research problem 1. We're going to talk about the two-dimensional discrete Fourier transformation and basically apply that to MRI example. Basically, a simple data set that I collected myself a long time ago. And we're going to basically use it as an example to better understand the Fourier transform and the reconstruction process from the Fourier transform domain to the spatial domain. Okay? And I'm going to talk to you about two interesting applications that are related to MRI image reconstruction, which are motion artifact suppression and partial Fourier imaging. So do you have a particular idea? Maybe, okay, this is not, just a second, maybe I should just delete that. Okay, maybe I'll just, it's from last lecture. So to get started on Fourier transform, basically we have to start from the one-dimensional Fourier transform. Okay? So basically we're just gonna talk about 1D, continuous time. Fourier transform. Okay. Basically, the equation for that was basically f of omega is equal to integration from minus infinity to infinity, f of t, e to the minus j omega t dt. Basically, we're going from the time domain designated by t, the variable t, to the frequency domain and in this case, the variable for it is omega. Okay, there are several properties of the Fourier transformation that I would like to understand first before we proceed further to use it. Okay, first of all, the Fourier transform is a linear transformation, which means that it basically satisfies the superposition properties. Superposition. Basically, it means that you have to have additivity. You have to have scaling. Let's talk about this a little bit further. Basically, if you talk about basically the additivity, basically if we designate the Fourier transformation operator as Fourier of whatever is in here, if I have a Fourier transformation of F1 and the output was capital F1, we usually use this particular notation where the capital letter designates the frequency domain function and the small letter designates the time domain function. Okay, so if I have that, and if, for example, if I have another one, if I have another function F2, and basically it comes out as F2, then I add them together. If I have the Fourier transformation, if I try to compute the Fourier transformation of F1 plus F2, it will come out like capital F1 plus capital F2. Okay, and basically this is the additivity. Basically this is the additivity part. This is very useful, of course, because basically if it wasn't like this, then things would be very complicated. It would be really difficult to compute the Fourier transformation. Now, if we have the Fourier transformation of a few basic functions, we can compose a very large number or a very large set of other functions that are composed by superposition or adding these basic functions together to basically come out or come up with the Fourier transformation of the summation. Related to the scaling, basically it means that if instead of having F1 here, if I have F1 times alpha times a constant, then it will come out like alpha times the Fourier transformation of this basic function. Okay, so basically, if you multiply the function by a constant, then the Fourier transformation will be multiplied by the same constant. So this is really useful. Okay, so if I have two functions, if I have two various different signals, and compute the Fourier transformation for each one of them, I can compute any particular or any weighted sum of functions using this linearity. Is that clear? Is this property clear to you? Is it clear?
Yes, doctor, it's clear.
Okay. So the second one is as follows, basically. It's a very important property. Basically, we call it an orthogonal transformation. You know what is the meaning of the word orthogonal? What is the meaning of orthogonal?
Perpendicular.
Basically, it's like if you have two lines like this and the angle between them was 90 degrees, we call these lines orthogonal, right? But actually, orthogonal has a more general meaning than that. Okay, orthogonal transformation, it has basically it preserves two things. It preserves angle and preserves length. Okay, for example, I'll give you an example of orthogonal transformation. Very simple example. You all know about this example. Basically, if I have basically let's just write the axes or draw the axes like this. Basically, you have a vector that looks like this. Okay. And basically, this vector actually makes a 30 degrees angle with this axis, with the x-axis. If you apply a rotation to this particular vector, okay, let's just call this vector x. It's not a good. Just call it v. Okay. If I apply a 30-degree rotation to this vector, it will come out like this. Where actually this here is, the angle here is 60 degrees, right? Let's just call this V dash. The operation of rotation here, the thing that I did here, the rotation itself, did it change anything related to the length of this vector? If I rotate this vector here to become here, do you think the length of this vector will change when it's rotated?
No.
Okay. And imagine that you have another vector here. Let's just have another vector. For example, let's just make it like this. And basically, let's just call it V2. Okay. And basically, these two had this V and V2. Basically, let's just call this V1. V1 and V2 had an angle of 90 degrees between them. If I rotate this V2 by the same angle I rotated V1, what would happen? Basically, this was here, and basically, if this is 90 degrees, this is 60, this is 60, right? The remaining angle here would be 60, right? Because the sum of these two angles would be 90 degrees, right? So if I rotated this vector by 30 degrees, just like I did to this one here, it will come out like what? Like something like this. This is V1 dash, and this is V2 dash. Basically, I rotated this to this here by the same angle I rotated this to this. So basically, these two, V1 and V2, were rotated 30 degrees counterclockwise to become V1 dash and V2 dash. What do you think the angle between V1 dash and V2 dash will be? After I rotated V1 and V2, it will be exactly 90 degrees. So basically, the angle here also will be 90 degrees. So basically, rotation is an example of orthogonal transformation. Why is that? Note the angle. If you rotate everything, if you apply the rotation to everything, the angle between different things will remain the same. If I apply it to two vectors, if these two vectors had an angle in between them of 90 degrees, it will remain 90 degrees. If the angle was 70 degrees, it would remain 70 degrees, and so on. Okay? So basically, we're talking about we're preserving the angle. After the transformation, the angle was preserved. Okay? The second thing here is the length. Do you think after I rotate this vector to that one here, to V2 dash became V2 became V2 dash. How about this length and this length? Are they the same? When you rotate things, will it change length, or would the length be the same? I'll give you another example. Just imagine that you're holding a pen in your hand, okay, and you're rotating that pen. If you basically measure the length of the pen when it's horizontal, does it differ when you basically rotate that pen to become vertical? You expect the length of the pen to change when you rotate it? It doesn't change. So basically, this transformation doesn't change the angle or the length. So basically, we preserve these. Okay, so any transformation that would preserve the angle and the length would basically be called an orthogonal transformation. The Fourier transformation is like that, meaning that if I compute the Fourier transformation of a particular signal and compute it for another signal, the relationship between the two signals in the time domain will remain the same as the relationship in the frequency domain. The angle and the length might not be clear to you, but actually the length can be very simple as Euclidean distance. If you have a vector that looks like, basically, if you talking about the length, for example, if you have basically x and y, a vector that looks like this, the distance or the length would be as simple as square root of x squared plus y squared. If I take this vector to the frequency domain and it became capital X and capital Y, the length would be square root of x squared plus y squared. Okay, and basically the orthogonality of the Fourier transformation tells you that these two are equal. So basically, when you're taking the signal to the frequency domain, you're not taking the signal. You're basically looking at a different version of the same signal. It has the same properties. It did not lose the properties that were originally present in the time domain. It's just another way of looking at it. Imagine that you're holding a cube. Okay, when you're a cube, okay, basically when you rotate it, you see different faces each time you rotate. You cannot see all the faces of the cube at the same time. Okay, but is it different? No, it's basically looking at the same cube, but different views of the same cube. Okay, it's exactly the same as the Fourier transformation. So I would like you to understand that basically the time domain version and the frequency domain versions are basically two sides of the same coin. They represent exactly the same thing. It's just a different view of the same thing. Okay, so basically for MRI in particular, or in the other modalities where basically you're acquiring the data. For example, if I wanted to collect a particular signal, S of t, okay? Basically, I can collect it in the time domain, or I can collect it in the frequency domain. Basically, in this case, I will be acquiring S of omega. And basically, once you acquire one of them, you have the other. This relationship is unique, meaning that some people like to call it one-to-one. One-to-one means that once you have a particular signal here, it has only one signal in the other domain. You cannot have two signals going to the same Fourier transformation. So if you imagine that S1 of t, S2 of t go to S of omega, this is incorrect. If these are different, if these two are different, they cannot have the same Fourier transformation, and the other way around. If you have a particular Fourier transform or a particular Fourier spectrum, you have only one signal to return to. You cannot have two signals. So it's unique. So basically, we can collect the data in the time or frequency domains, and it would be just as good. Why do we choose time or frequency? Can you answer this question? When do you collect the data in the time domain, and when do you collect it in the frequency domain? Anyone with an answer to this question? Let me write it down. Question. When we choose to collect data in time domain, and when to collect it in frequency domain. Can you answer this question?
Maybe when it's continuous, I collect it time domain.
Actually, in reality, both are continuous. We have to sample whatever. If I'm collecting in time, I have to sample in time. If I collect in frequency, I have to sample in frequency. We cannot collect continuous time. And the reality of all signals, or real signals, are basically continuous. None of them is inherently discrete. Any other answer? Okay, let me give you the answer. And this is what we're going to see in MRI now. Basically, we collect in the natural domain of data. What is the meaning of that? In some applications, like for example, in ultrasound imaging, the data collected, the data is coming from basically samples of. On the other hand, in MRI, the data are coming as samples of frequency domain. So basically, the signal that you're collecting, the signal that you're measuring in MRI, basically it's just a sample or set of samples from the frequency domain of the image that you're trying to collect. This is by definition. So in other words, you're collecting in the easiest possible way, basically. Whatever the data is coming from, basically, or if the data is present in the time domain, I sample in the time domain. If the data is coming in the frequency domain, then I collect it in the frequency domain. Basically, it's just a matter of convenience because basically they are equivalent. Basically, if I collect it here or there, it's fine. I don't have to convert it. If, for example, for the MRI, I don't have to convert the data of MRI to the time domain to sample it in the time domain. No, I actually collect it in the frequency domain, and I know how to go back from the frequency to the time if I want. Okay, so let's continue on that a little bit further. We were talking about one-dimensional signals. Okay, we're talking about one-dimensional signals. Okay, how about if we take it to two-dimensional signals? What is an example of a two-dimensional signal? An image. Okay, two-dimensional signals means that you have something like this. You have two axes, x and y, and you have a value for each one of the values of x and y. So you have f of x and y. Okay, here for one-dimensional, basically we're talking about a signal, whatever it looks like this, just one axis, time. Okay, and we have a signal here, f of t. So now when we're talking about an image, first of all, we talk about spatial domain, not time domain. So basically this is spatial domain. Because the axes here are space, x and y. Here, basically we're talking about temporal. Basically the axis is time. Okay, but it's exactly the same. The Fourier transformation is a mathematical transformation. Meaning that basically you have if you have time here, you go to a frequency, and this frequency has units of 1 over time. If I have one-dimensional Fourier transformation, but it's actually from x, this is space, this is units of seconds. Okay, this is 1 over second, basically this is 1 over second, which is basically hertz. Okay, if I have x with units of meters, I go here to basically I say fx. Okay, and frequency x, spatial frequency x, and this has units of 1 over x, which is basically 1 over meter. Doesn't have a nice designator hertz, but it's actually 1 over meter. It's exactly the same as what you have here, 1 over second. So basically whenever you have a variable here, the frequency will come related to that variable. If this variable has a unit of meter, the frequency will be spatial frequency, and basically it will have units of 1 over time, 1 over space, 1 over meter, basically. Okay? So basically, it's a mathematical transformation, and it takes from one domain to another. This domain has whatever units you want. The other domain has 1 over that unit. Okay? So this is basically, this is not an issue at all. This is not a problem. But how about two-dimensional? Two-dimensional, we basically extend the same definition of the Fourier transformation to have both, basically. So basically you have f of fx, fy. Okay, before we proceed with fx, some people prefer, or some people, at least in the MRI community, they like to call this kx. Instead of fx, they call it kx. Okay? And basically they call the frequency domain, they call it the k space, because it has kx and ky. Okay, you just like it as a notation. Basically, it's a notation that was really popular. People actually are familiar with it more than any other notation. So basically, here, if we have this definition here, then it will have basically f of kx and ky, the frequency variables, will be equal to, instead of having only one integration, we'll have two. You will have here f of x and y, and you will have e to the minus j twice pi k x x, e to the minus j twice pi k y y. Basically, remember that omega was twice pi f. F was the frequency in hertz. Okay, remember this. So basically, if I wanted to apply the same thing here, kx will correspond to this f. So if I wanted to have omega x will be twice pi kx, and omega y will be twice pi ky. So basically, it's going to be like this, dx dy. Very similar definition to what we had in the one-dimensional case. Okay, how do we compute that inside the computer? This is an integration. Okay, so basically the continuous domain in general, any continuous domain you cannot really deal with in a computer. So basically in computer, no continuous variables. And let's just call it, or no real numbers. What does that mean? No continuous variables, because basically, even if I have one-dimensional signal, basically if I have, this is time, between the point of 0 seconds and 1 second, how many samples do we have here? How many points do we have here? Between 0 and 1. How many points do we have? This is continuous. Infinite. Why? Because basically if this is continuous, then if you give me 2 points, I can get you another point in the middle. Okay? If you take this one and this one, you can find one in the middle. So basically you can keep doing that forever. Okay, so basically you have an infinite number of points between this point and this and that. Another problem is basically even if you can sample, basically if you just decide to basically take samples instead of just taking the all the points, basically I'm just gonna take this point, this point, this point. Basically that's it. You just take 3 points. Would that be enough if I take just 3 points? Would that be enough to have it in a computer? Would that be enough? If I do sampling, if I just take this and do sampling, just sample this so that I can have a finite number of points. Would it be enough if I have like 3 samples, finite number of samples, to have these samples inside the computer? Just give me your opinion, just whatever you think of. You don't have to be sure that you have the right answer.
Yes, it is enough.
Okay, this is okay here.
No.
Because basically you have no continuous variable, you have now discrete variable, but the problem there is that now you have real numbers. If you try to represent each one of these points, how many bits do you put these points in? Remember the quantization thing that we talked about? Remember the quantization? Quantization you did in assignment 1? What did you do in the quantization? Quantization, you took real numbers and represented them in a finite number of bits. Okay, basically not just having finite number of samples. If each one of these is a real number, real numbers have infinite resolution basically, because basically if you, for example, take this example here, you're going from this level to that level. If you try to represent this as a real number, then any value in the middle here should be represented. This is a real number. Okay? If each one of these variables, each one of these values should be represented in your number, then you have to have infinite number of resolution, number of bits. Because basically here, you have infinite number of points, infinite number of levels. So basically you have to have finite number of bits. Okay, so once you sample, once you do sampling and quantization, you can take everything inside the computer. Okay, basically an image is just a sampled version of a continuous two-dimensional function. An image is a sampled version of a two-dimensional function, basically in the spatial domain, basically. So an image is, maybe you can say also a quantized and sampled version of a two-dimensional continuous domain function. Another thing that we forgot to talk about, maybe put it number 3 here, it has to have finite support. Finite support means that you start from here, you end from here. It's not from minus infinity to infinity. Finite support means that you cannot have something that has an infinite duration, which makes sense. Okay, so basically finite support. You just have this as a finite support. Okay, so basically, if you have that, you can actually have something that can be represented in a computer. How can we compute the Fourier transformation for a discrete, or basically this whole version here, we call it a digital image. If basically an image satisfies all these quantized, sampled, and finite support, we call it a digital image. Okay. How can we take a digital image and compute its Fourier transformation inside the computer? Basically, we have to go to the theory of discrete Fourier transformation. For discrete Fourier transformation, basically, if you try to compute the Fourier transformation with the integral, basically f of omega, like what we talked about before, f of omega, continuous Fourier transformation, f of omega, we can just write it this way, f of t goes to f of omega. Okay. Usually we have this as two-directional vector like this, because actually you can go back and forth. This is forward Fourier transformation, and this is backward Fourier transformation. Continuous Fourier transformation, you have this as continuous function and this as continuous function. Basically, you cannot compute that in a computer. Okay. How about if we sample this? If we sample this, we call it discrete time Fourier transformation. We start from f of n, basically instead of just calling the function, because we did sampling. So basically you have number of samples here. N is 0, 1, 2, 3, and so on. It's not a continuous variable like t here. If you take the discrete Fourier transformation, basically, as long as you have sampled version here, you're going to have a Fourier transformation here that comes as f of omega. It's going to be continuous, but actually it's going to be periodic in the frequency domain. If you basically do the opposite, if you have a signal here that is basically, if you just call this as, if you have this hat here, means periodic, okay? Then if you have something that is periodic in the time domain, it will come out on the other side as sampled. This is one of the properties of the Fourier transformation. We call this actually discrete Fourier series. So basically sampled from one domain becomes periodic in the other domain, and the other way around. If you have it sampled in one domain, it will come out periodic in the other domain. If you have it periodic in one domain, it will come sample in the other domain. Okay? So basically, Yeah, go ahead.
Period does mean it repeats itself for a specific period or not?
Yes, it's repeated with a certain period. So basically, if you have this period, anything outside this period will be repetitions, basically. I'm
Okay,
going to
thanks.
show you an example right now. Yes. So basically, if you look at these, in each one of these versions of the Fourier transformation, this is the continuous Fourier transformation, the discrete time Fourier transformation. It's a special case of this one. This is a special case of the original. And this is also another special case of the original. The continuous transformation, continuous Fourier transformation is the basically, you can call it the most general form. Any other Fourier transformation will have to be a special case of it. So in each one of these, here you have a continuous function, and continuous function, we cannot have that in a computer. Here you still have a continuous function. You cannot have that on a computer. Here you still have a continuous function. This is periodic function, but it's continuous function. You cannot have that in a computer. So basically, in order for us to be able to do something on a computer, we have to actually apply these two together in one domain. If I have a signal here, let's just call it f of n, that is basically both sampled and periodic, it will come out on the other side as f of n or f of k, and this f of k will be periodic sample and periodic as well. And we call this discrete Fourier transformation. And this is what is practical for a PC. Because basically here you have a sampled version, and here you have, because it's sampled, here it comes out as periodic. Because it's periodic here, it will come here as sampled. So as long as it's periodic and sampled, you can deal with it in a computer. Basically, if this is periodic, it means that it goes from minus infinity to infinity. But actually, as long as you talk about one period, if you compute only one period, if you use only one period here and one period there of the periodic function, then you can have a transformation that is basically achievable on a PC. Okay, so the idea here is whatever I have, if I have a particular signal that looks like this, for example, okay, this is my signal. Okay, I don't have any other samples. Basically, I started collecting data here and I stopped here. I took basically 101 samples. Okay, that's it. This is a sample signal. Okay, basically, I don't know what's here. I don't know what's gonna come out there. I don't know what happened before or after that period that I collected. This is the data collection I have. Okay, so if I have only this, what should I assume before or after? Actually, it doesn't matter. Why? Because basically I don't know of that, and I can assume whatever is more convenient for me. So the discrete Fourier transformation will assume that you have periodic extension of this function here. And basically, if you assume that, basically, what's going to happen is that it will simplify things for you to a great deal, and it will make it possible for you to do that in exactly the same in the Fourier domain. If I, for example, took this in the Fourier domain, I take this part here and basically compute the frequency domain equivalent of it. Let's just call it, maybe I should put it like, for example, it will look like this, okay? For example, okay? If I take this, basically, here also, the assumption of periodicity will also hold. So basically, here I'm assuming also that beyond these 2 points, beyond the period that I computed, there will be also repeated versions of the same function as I have it here. So this is an assumption. You will never see it except when you have something wrong. Okay, so if I compute the Fourier transformation of any signal, you will see only one period from the signal in time, and what comes out from the frequency domain or the Fourier transformation will be basically another period, or a period of the frequency domain of this particular function. When I do something wrong, I will see the periodic extensions in this case. I will show you some examples. We have to actually do some practical work here so that we can understand it. Without the practical examples, we will never be able to do that. Okay? So basically, before we do that, let me give you some relationships between the sampling here and the sampling there. Basically, in the sampling of the frequency domain, of the time domain first, basically I start from this sample here. I take different samples. Okay. For example, this is my sampling duration. This is sample 0, 1, and so on. This is n minus 1. If I have n samples, I have n samples. Okay. Basically, I have to have something called sampling periods. Okay. Of course, you heard about that in the signal and systems course. The sampling period is by definition 1 over the frequency sampling. If I have sampling frequency, particular sampling frequency, the sampling period will be basically 1 over Fs. This will be in seconds, of course. This length here is called the sampling duration. Let's just call it T, designated as T. It's equal to n Ts. Basically, you have here n samples, and each one has Ts between the sample and the one before and the one after. Okay, so this is the sampling duration. Okay. For some reason doesn't write. Okay. Basically, this is sampling duration. Sampling duration, this is the period where I basically collected all my samples. This is the sampling period. This is the distance between each sample and the next. Okay, so when I take these, I take these samples, these are going to be an n-dimensional vector here. Okay, so n samples here should be like a vector. I will do the Fourier transformation. Okay, and basically let's just, instead of writing the Fourier transformation this way, let's just say that it's DFT because it's the discrete Fourier transformation in particular. So we will come out, what will come out from the other side will be basically something very similar. We'll have sampled vector. Basically, it's going to look up like this. Basically, we'll have an n sample vector, but this vector in the frequency domain. Okay, the numbers from here 0 to ns minus 1 or n minus 1. Okay, basically, n here is exactly the same n as here, the same. But here you have different sampling periods. Basically, the distance here will be delta k. We decided that the variable here will be k. Okay, so it's delta k here, and basically the whole thing in the frequency domain is the bandwidth, which is equal to n delta k. There are some fundamental relationships between delta k and bandwidth, and the other side, the Ts and T. Basically, you have a relationship that basically have a crisscross like this. You have a relationship between delta k and the sampling duration, and you have a relationship between Ts and the bandwidth here. Okay. First of all, delta k will be equal to 1 over T. Okay, which means that it's basically 1 over n Ts. On the other side here, the Ts on the other side, Ts here is equal to 1 over bandwidth. And actually, you find that basically the bandwidth here is actually equal to Fs. We'll find that basically it has to equal to the Fs because basically Es is 1 over Fs. So you have a reverse relationship between the sampling period in one domain and the duration or the bandwidth on the other domain. And it's an inverse relationship. Okay, this is extremely important because we know that if we don't use Fs, if you don't use sufficient sampling frequency, you will end up having aliasing. Aliasing is basically the following. Let me show it to you. Okay, let's just go with the examples first and then come back to this point again. Okay, so I'm going to start code here. Not this one. Let me just run one code. This is basically the essential code that I gave you at the beginning. Just wanted to change the folder. We don't really care about what comes out for now, at least. We're going to run it shortly. Okay. So basically, let's just imagine that you have a very simple signal. X is equal to zeros of 101. Okay, 100 by 1. Okay. This is basic time domain signal. Okay. I'm just going to put X of, for example, 1 to 4 equals to 1. So basically, you have only 4 points. Let me just make it 8 so that it becomes a little bit clear when we draw it. 1 to 8 is equal to 1. So basically, it looks like a gate. Basically, you have 8 points as 1, and the rest of the points are zeros. In order for us to compute the discrete Fourier transformation, we use DFT or FFT. Basically, here in MATLAB, DFT is called FFT. We'll have capital X is equal to FFT of X. And basically, frequency domain by definition, it will come out on the other side as complex numbers because it will have two components. It will have absolute, it will have basically magnitude and phase. Okay? So basically, if we do that, basically, maybe you should have a two-dimensional example first. I'm not sure. Maybe I'll have two-dimensional example first. Have you done any Fourier transformation experiments on MATLAB before?
Yeah, using the signals.
Yes, but I mean the other guys. I'm sure you did, but the other guys, I'm not sure they did something like that. Okay, that's fine. That's fine. We'll do that here. Okay, so we'll just draw that here just to see it. If you remember from the Fourier transformation theory, if you have a gate, the Fourier transformation will look like a sinc function. Sinc function is basically sine x over x. So it will look like a sinusoidal signal, but the amplitude keeps going down from the first point to infinity. So let's see that. Subplots of say 4, 1, 1 plots of x, so that we see how x looks like. And we will plot capital X. But actually, as I was telling you, basically the outcome will come out like complex numbers. We cannot plot complex numbers, okay, because basically it has magnitude and phase, or it has real number, real or imaginary parts. Okay, so we cannot have each one of the points having two values. We have to have each point in the plot having only one value. So we can choose to either plot the magnitude or the phase. So basically, I'll plot both. The magnitude is computed using absolute value, and the phase is computed using a function called angle. If you have a complex number, maybe I can show it to you here. If you have a complex number, Basically, I can say x equals to 1 plus I. Basically, MATLAB accepts I as the I that we know, or J. You can say J, okay? It's fine. Accepts both, actually. Both are equivalents. J and I represent the basic square root of -1, basically the imaginary, or the basically the imaginary variable, basically. So basically, if I have absolute value of x, it will come out like square root of 2, 1.4142. Here, if you have 1 and 1, imagine this is like a vector making an angle of 45 degrees, right? So if I say angle of x, it will come out like this. This is basically pi over 4. If you don't, maybe you can just multiply it here by 180 over pi, that we can see it in the right way. So basically, absolute computes the magnitude of the variable, of the complex value. The angle computes the phase of the complex value. So now I'm going to do that for both. Let's see how that looks like. Okay, we need to have this x6 code. Okay. Does this look like a sinc function? Actually, it doesn't, because actually sinc function should be basically, if you imagine, it looks like, if I have, from the theory of the Fourier transformation, if I have a signal that looks like this, just a gate, okay. This is time, basically. You have 0 in the middle here. Okay, this will go in the frequency domain if you compute it from basically, if you look up the function of the Fourier transformation, the continuous transformation of a signal that looks like this, to come out like this. I can write it. I'm sorry, I cannot draw it properly, but this is a sinc function. We call this a gate function. So basically, the 0 frequency will correspond to the maximum here, okay? And here will be negative frequency or positive frequencies here, and this is negative frequency. So this is frequency domain. Okay? So if you look at this and compare it to this figure here, let's look at both. How do you relate this second plot here? This is supposed to be the magnitude of the frequency domain. Why is it different from this one here? Why is it different?
Positive side.
Is it what?
Positive side.
Okay. Okay. Basically, okay, I'll probably show it to you here. Basically, imagine that, or basically remember the periodicity assumption. Okay. In order for us to apply DFT, we have to have that periodic and that periodic as well. So this one here is actually, the computer thinks it looks like this. And there's another one here. So basically, it's the same function here, but repeated. It thinks it looks like this. So this is the first thing that the computer thinks. The second thing is, we are used to looking at the frequency spectrum from minus to plus. Okay, so for example, if you have here, if you have n samples, we are used to looking at the samples from minus n/2 to n/2. What the computer gives you is not like that. Basically, what the computer gives you is something that is basically from 0 to n. From 0 to n. Okay? So it means that the 0 is not in the middle. Okay, let me show it to you again here. See here? It's exactly the same, but actually the second half is basically here. What you're seeing is this part right there. Let me draw it for you here so that you can see it. What you're seeing on the computer on the plot that you got from FFT is this part here. How do you get from this part to something that looks like this? You need a shift. Instead of displaying the window from 0 to n minus 1, you need to display it from minus n over 2 to n over 2. So you can do that with a very simple function called Fft Shifts. Okay, so instead of just using FFT, I will use also Fft Shifts. This will basically shift the samples so that the 0 is in the middle. So if we do it like that, just add this function right there. See now? Looks exactly like the one that we saw before. Let's just forget about the phase for now, okay? Because the phase is very complicated. We're going to talk about it when we talk about the MRI samples, okay? So how about this? Looks okay. Looks very good, actually. Looks like the theory. A very well-known characteristic of or property of the Fourier transformation is that the bandwidth in one domain, say the time domain, times the bandwidth of the signal in the frequency domain is a constant for a particular signal. Meaning that if the bandwidth here increases, this will have to decrease. Okay? How can we define bandwidth in this particular signal that we have? Obviously, the bandwidth here is just the width of this pulse. The bandwidth here, if you take it as the 3 decibel bandwidth, is going to be basically the width of this main pulse or the main loop here. Okay, so this width here corresponds to the width in the frequency domain, bandwidth in the frequency domain, and this will correspond to the bandwidth in the time domain. How about if we try to make this larger? Instead of having this as 8, we make it as 16. What do you expect to happen in this the frequency domain here? Would it be larger or smaller? I made this larger, I will make this larger. Expect this to be larger or smaller? Based on the equation that I just told you. If I make this larger, this has to be smaller so that the multiplication will be constant. Okay, let's try that. Before we do that, just basically it's roughly from this to this, it's about 20 something, right? Because this is 14, this is 6. Okay, I'm going to increase that by a factor of 2. So I'm going to make that, instead of 8 here, I'm going to make it 16. How do you like that? When this increased, this became half. This is like about 45. This is about 55 or 56, something like that. So basically, the width of this main loop became half. How about if we increase that a little bit further? If we increase it a little bit further, what's going to happen? This will be even more smaller. Okay? So if I make it 32, now much smaller. How about if we make it 4? If it's very small, then the width will be much larger, as you see here. Okay, so there is a relationship between the signal here and the signal here. In all cases, if you have the frequency domain, you can go back and compute the time domain again. Let's try that. Basically, I'm going to have X reconstructed is equal to, basically, if I do it this way, then I'm just going to use exactly the same thing here, but in the opposite order, basically. I'm going to do Fft inverse Fft of Fft shift, because basically I'm going to reverse it. Basically, I'm going to take that to the other side and that to the other side after that. Since I took the output of Fft and made Fft shift, you apply it twice, you get exactly the same original thing. FFT shift basically shifts a spectrum by n/2. If you shift it by n, it will not make any difference because the period is n. So basically, if I do it this way and put capital X in here, okay, what's going to come out will be basically exactly the same signal as the original. XR. Okay. Usually you put it as absolute value or real value, it doesn't matter because actually it has to be real. Sometimes it's for the numerical errors because you're going back and forth with the computer, maybe you can just use it without absolute value for now. Let's see if it comes out weird. Okay. Calling function, indexing a variable. Okay, sorry. Parentheses and how do you like that? What came out here was exactly this one. So basically, I computed this one here from basically the spectrum, not from the original one. So I can always take this and go back and get that. Okay. What I'm going to do now is I'm going to try to basically try some of the sampling issues that we talked about, just the relationship between the samples, the time, and the frequency domains. Okay, imagine that the original signal, just make it 8 here, like this. Okay, imagine that the original signal was like this. Okay, that just looks like this. Okay, what would happen if I basically undersampled this signal? If I basically took every other point, okay, what would happen? What do you expect to see there? If I undersampled this part right there, what would happen on the other side? Okay, you had problems understanding the theory of Fourier transformation, or if you have any question, please ask. Okay. Okay, I'll tell you what. I'll show it to you practically. Okay, so that you can understand it a little bit better. Okay. So what I'm going to do now is I'm going to take the first part of the code that I gave you, the sample starter code that I gave you at the beginning of the research problem 1. It has a part where we basically read the file where I put the Fourier domain of an MRI image in it and basically compute a Fourier transformation for it. Let me just get this code until the end. Okay. The bandwidth, I think it's still here. Basically, this code has the first part here reads the data from this file here. Okay? So basically, the data here looks like this. Basically, just samples. Each line has 2 numbers. One of them is the real number. The other one is the imaginary number. So each line contains a sample of the frequency domain. The MRI, in particular, as a particular example, as I told you, basically the natural data domain is the K-space. You have here Kx, you have here Ky. Okay, basically in the frequency domain or the K-space of MRI, you can design any sequence, what you call MRI sequences. each one of these sequences collects the frequency domain in a particular way. The one we have collects the k-space as lines like this, samples on particular lines. But actually, there are sequences that collect the data space as spirals, as radial lines, things like that. So there are several of them. Some of them actually collect it as zigzag, like this. But actually, as long as you cover the same area, you can actually reconstruct an image. So basically what we have are samples from here. Basically, the signal that comes out from the MRI machine will be basically will correspond to one of these lines. So basically, I sample the signal and basically place it here in the corresponding line. I keep doing that for each one of these lines until I cover the k-space area that I want. Okay, so the sampling here, sampling I do for MRI signal is actually sampling in the frequency domain. And actually there are two basic sampling schemes that have to be done. One is done in this axis, in the kx, and one is done in the ky. This one here is called the readout, because actually as you read the data, you sample the data by this readout sampling. The other one is what you call it, the phase encoding. You basically choose the step here, so that basically if you take a line, if you take the sample here on one line here, okay, these will be basically sampled by the space between each one of these lines, which is basically one of the things that we set in MRI, which is the phase encoding. Okay, so we have two sampling that are done there. The data I gave you, the data you have from the research problem 1 data, were collected the right way. You have the full data. But we're going to try to see what is the effect of undersampling here or undersampling there, and basically try to understand what's going on. Okay, so let's run the code and see what happens. I'll show you the results first and then go with you over the code. Okay, maybe I should just close that first. Okay, so first of all, in figure 1, I'm sorry, let's just do it again. Maybe I should just come in this part for now and have close all. Basically, what I have here is the k-space data. This is what I got from the data. Basically, this is basically what you have from the original data that I gave you. When I take these data, these are real numbers, these are complex numbers, just take the absolute value and just draw it here. You will always find that the center point, the DC value of the frequency domain that corresponds to kx frequency 0 and ky frequency 0 will be the highest intensity point in the k-space on the frequency domain. Okay, the k-space itself doesn't really look like anything you know. It's very difficult to interpret the actual shape or appearance of the frequency domain. But if you take this and apply an inverse Fourier transformation, you will find that you can get an image right away. So basically, if you do that, you get an image that looks like this. So basically, this image came out by very simple inverse discrete Fourier transformation of the original space. Looks like an image, looks like an image that looks okay, doesn't have any problems. Let's forget about these two for now. Basically, if you take an image and sample it the wrong way, you come out to something that looks like this. Why do we see something that looks like? Basically, when we undersample, you will have aliasing. Aliasing means that on the other domain, the periods will basically overlap. Let's go back and explain this a little bit more. Basically, imagine that I'm in one domain Imagine that I have a frequency domain, or let's give a time domain example first. If I have a time domain signal that has a frequency domain with a spectrum like this, this is continuous. Continuous means that it's like this, it doesn't have any periodicity. When I sample it, this signal, whatever, okay, if I sample this signal, okay, what's going to happen is that I sample by Fs, and this Fs will determine what? Will determine basically the bandwidth here. You remember? Okay? If I have Fs equal to the bandwidth of the signal, then the periodic extensions will be fine, will be far away from my original one. So basically, the periodic extensions due to sampling will basically not overlap the original one. So basically, the original one will look okay. How about if we take Fs over 2? I take half of the proper sampling frequency. In this case, what's going to happen is that when you start with a signal that has a frequency domain that looks like this, what's going to happen is that it will have basically this Fs is the period of the periodic extensions here. So if I have Fs over 2, it means that these periods will not start from here. No, it will start a little bit earlier, so it will start here. Okay, and this here will start like this here. So you will have overlap. If you try to look at the original bandwidth here, you will have an overlap from the period from the left and period from the right. Okay, what happened here was exactly that. What you saw here is exactly that. This image, the original image that we were looking at, basically this is just one period of a periodic signal. This is actually periodic in this direction, in the y direction, and in the x direction. So there is another image that looks like this here. Another image that looks like this here. If I undersample in the frequency domain, it will alias. This is called aliasing. Okay, this is aliasing. It will alias in the frequency domain. It will alias in the time domain. If I undersample in one domain, it will alias in the other domain. Alias means the periodic extensions will overlap the original. And it doesn't matter where I undersample. Basically, if I undersample in the time domain, it will basically alias in the frequency domain. If I undersample in the frequency domain, it will alias in the time domain. It depends on where I'm undersampling. So because I undersampled in the frequency domain, the spatial domain came out undersampled, aliased like this. Aliasing means that the periodic extension, basically imagine that this one here, this image here had another one here, another one here. Due to the undersampling, it came and basically overlap the original one. And whenever you have aliasing, you cannot recover. So aliasing is not an artifact that you can remove. Basically, it's a destructive artifact. If you have an aliasing in one image, you have to basically repeat the imaging again. So you have to be sure when you're sampling in the frequency domain, in the k-space of your data, you have to be sure that you're sampling the right sampling frequency. Otherwise, you'll end up with an image that is not usable like this one. Okay? So basically, this is an example of how you would sample, or basically how you would simulate aliasing artifact in the original data. Basically, undersampling is very simple. If you have data, if I have an original signal, it doesn't matter if this signal is in the time domain or the frequency domain, it doesn't matter. If you have a signal that looks like this, basically. Okay? basically this is assume that this is sampling with Fs. If you want to have a signal that is sampled with Fs over 2, you basically take every other sample. If you do that, basically you're doubling Ts. Ts dash will be basically twice Ts, meaning that 1 over Fs dash basically is basically half of the original Fs. So this is what we did here. All we did here was just, instead of taking all the samples, we took only one of each two of these. This can be very simple, actually. If you have an array, f of from 1 to n, for example, all you have to do if 1 to n is equal to, for example, index, okay, this array is from 1 to n, you basically take f of n, f of 1, 2, n. That's it. You start from 1 with a step of 2 until you reach the end. Let's try that so that you can see how it's done in a one-dimensional signal. I have, let's have X as a sinusoidal signal. Okay, sinusoidal is okay. Maybe I should have something that looks a little bit, I just want to see the effect of the undersampling a little bit more, but it's okay. Sine pi over 10 times 1 to 100. Okay. And basically X undersample equal to exactly the same thing here. Instead of having 1 to 100, it's 1 to 100. And let's draw that. And let's pause here so that, or maybe I don't want to execute the rest here, so I'm just gonna F0 so that it doesn't run, so that I see that only. See now, first of all, the number of samples now in the undersampled signal became 50. The sampling inside the sinusoidal signal doesn't really look right. Okay, it doesn't look as good as this one here. We can undersampling a little bit further so that we can see that effect. If I, for example, undersample by a factor of 4, now I'm taking one sample each 4 samples. Let's see what comes out. How do you like that? When you have aliasing, basically what happens, you're sampling a perfect signal, and the samples that you have, because you have undersampling, you have not enough samples, you do not have enough samples, you end up with something that doesn't represent the original signal. And this will go in the other side and represent something that would have aliasing, that would have the spectrum of the original signal superimposed on its aliases, on its periodic extensions. Okay, so basically when you do that, when you undersample, basically you end up with something, you can end up with something that doesn't look right. The other one, the one that when we have 1 every 2 samples, looked a little bit distorted, doesn't look as good as the original, but it was okay. You can still see that it's a sinusoidal signal. Now you cannot determine that it's a sinusoidal signal from these samples. So basically, for the sample that I showed you here from the MRI, What I did was to do exactly this. Instead of just taking frequency domain data as it is in the correct sampling period or in the correct sampling frequency, I distorted that. I made the samples a little bit less. When you do that, you result in aliasing in the other domain. When you undersample in one domain, you alias in the other domain. Okay, so basically this is the key thing that you have to be worried about. Okay, so here in this part of the exercise, what we are going to do is to use the data that we have, that the original data that looks okay. We're going to try different things so that we can understand how the Fourier transform works. We can understand sampling, how sampling is supposed to be. We can also understand the value of the frequency domain, magnitude, and phase. Because actually we can basically, what comes out on the other side is complex numbers. The frequency domain is complex. Is it important to keep only the real numbers or the imaginary numbers or both? We'll find out that. We have found out that basically by experiments. We just try that and see the value of each one of these. We're going to see also that the effect of shifts in one domain will result in some phase in the other domain. So basically this will mean that we have, basically we can actually utilize that to have some research problems like motion artifact suppression, for example. If you have a shift, then the frequency domain will only have an additional phase. So if you can correct that phase, we can actually correct the motion artifact. Okay. Are you following me, or is it too difficult for you? Because it's sometimes the Fourier transformation is one of the topics that people don't really like, or basically they usually don't have a good background. Even if they took a signal and systems course, usually the signal and system courses that are taught in many places are theoretical, so people don't get the practical implementation or the practical value or the practical what to expect in reality when they deal with the Fourier transformation. Please ask me questions now before we proceed. If you have any questions about the Fourier transformation so far. Okay, so far no questions. Okay, we're going to proceed to better understand the code that we have. The first part of the code here is just basically a reader, just how to read the text file. Okay. I have to give it to you like this because usually when you get data from someone, if you have a particular machine, basically the data comes out like binary data. You cannot really read it like this. So what I did was to take the original image and write the data as a text file, like the one you saw here, so that you can see the numbers. Okay, so that it becomes clear to you that each point is two numbers. One is the real part, one is the imaginary. One very important thing, we all took medical imaging courses, right? In the undergraduate, right? Okay, how do we collect real and imaginary data? How do we collect, we know that we can sample a signal, okay? How we can sample, usually the signals are real. How do we collect imaginary data?
By using face, reading face and read out.
How do you read the phase?
Why is this okay?
Okay. Actually, it's a little bit tricky. It's a very tricky question, actually. What you have in MRI, for example, MRI in particular, You have the patient here, and the patient is sending signals everywhere. Okay? You usually have a coil here, coil there. This coil is X, this coil is Y. Okay? Because these coils have 90 degrees in between, they will collect data that are out of phase by 90 degrees. And basically, remember that the complex domain has real and imaginary, and they have 90 degrees in between. So basically, it's exactly the same signal. If you have a signal like this, we'll have a component here and a component there, and they are separated or different by basic 90 degrees. So if you collect the same data, collect the same signal using two coils, one in the x-axis, one in the y-axis, you can consider this as a real, and this is as imaginary. Okay? Why do we say that x is the real and not y? Actually, this is a trick question, actually. It doesn't matter, actually. Because basically, as long as you have 90 degrees in between them, it doesn't really matter. You can actually switch them. This is what I'm going to do right now. This is the first thing that I'm going to show you, okay? Basically, the K-space now is in the, or the K-space, as I told you, this is the frequency domain. So the samples are in the frequency domain. This is what you see here. Let me show it to you. This is the K-space here, okay? So basically, this responds to basically, this is real and this is imaginary, okay? No, I'm sorry, each one of these samples here are basically, each one of these samples has real and imaginary parts. And this is the x-axis, this is the y-axis. Each one of these samples is x plus j, y. If I wanted to switch x and y, what should I do? Basically, of course, I'm reading the data here as real numbers. I'm not reading the data here. The data here don't have I or j, right? They have I or j? You don't. Basically, I have a set of numbers here from the first coil, another set of numbers from the second coil, okay? So what I have now, what I did now is just have the first row plus j, the second row. That's it. If I wanted to switch that, I can do that. Very simple. Okay, so let's do that right now and see the image. Basically, I'm just gonna add 0 here so that we can just read the data and the image. Basically, what I'm going to do now is I'm going to take that. Let's call that K-space 1, and this is K-space 2. And for K-space 2, I'm going to multiply the first one by j and leave the second one as is. The difference between these two? So now I switched the coils as if I basically decided that my first coil is not the real one, the real data. It will correspond to the imaginary data, and the second coil will correspond to the other one. Okay, let me just so that you can see it clearly. Okay, so now we see I have j multiplied by the second one. Here I have j multiplied by the first one. And basically, let's compute two images. Image 1, image 2. And the first one is just K-space 1, and the other one is K-space 2. That's the Fourier transformation. This is exactly the Fourier transformation that we used before. We used on the one dimension, but actually, if you wanted to use it on an image, you have to use Fft2 and Ifft2. Okay. So basically, just add a 2 here so that it represents the two-dimensional Fourier transformation. And usually, you have to it's good actually to have Fft Shifts here and there so that you can see the image in the right format, but we can actually see how the image would look like if we remove the Fft Shifts. For now, let's keep it. Okay. Now for figure 1, what I'm going to do is basically I'm going to make two images. Yeah. Plot 1, 2, 1. to 2. This is image 1 and image 2. So let's try that. We're going to get two images now. The case space is exactly the same. I can put here case space 1 or case space 2, because basically I'm taking the absolute value. It's not going to make any difference because I'm displaying the absolute value. Absolute value will not look at the j. We'll take this square plus this square under the square root, so it will not matter. So any one would be the same. So now I took the data, the first column as the real, the second as the imaginary. Here I basically reversed that. I took the first column as the imaginary and the second one as the real. How do you like that? Do you see any difference?
It's like
what's the difference between these two? Okay, yes, it's basically just a rotation. Basically, because here, the configuration here, you assume this as the X coil and this is the Y coil. If you reverse things, then basically you will have a phase. You will basically the image as if you rotated the image. And basically it will look like something like this. Basically it's as if you rotated this a little bit. Okay, so is this rotated by, you know, can you tell me which angle do you have here? The angle between these two, the angle between this and this?
180?
It's about 180. Is it 180?
Right.
You see that it's 180?
Yes, doctor. 180.
Okay, why is it 180? The thing is, basically, if you have X here as the real part, okay? If you have this as the real part, this is now the real. This is the imaginary. Then you have a problem because the real is now, you don't have something that looks like this now. It looks like this now, real and imaginary. This is a little bit different. It shouldn't really appear like this. So it assumes that what you have here is the real that you have here is basically the other way around. It's used to real here. The real comes before imaginary. So it looks like this here. So it had to make that 180 in order for the signal to look the right way. Because you're assuming you always basically you always have the real part 90 degrees before the imaginary part. It came from this. Because basically it cannot be like this. It will be like this so that the real is before imaginary. It doesn't matter where they are, by the way. It doesn't matter if basically they are upright or like this, but the most important thing is that you have the real and then 90-degree phase and the imaginary. Okay, so basically it didn't matter. So actually it's still okay. It's still an image. You see an image, you don't see any artifacts. So basically it's just a matter of choice. It's arbitrary choice for you. You choose which coil you take the real part from and which coil you take the imaginary part from, and you still come up with an image. Both images are acceptable. Okay, it will not confuse the doctor. Basically, if the doctor sees the image to the right or to the left, he will know, basically. He will know that this image is rotated, which is okay. Rotation in this case is okay. So it's not a big deal. It's not a problem. It doesn't have any problem at all. Okay, so basically switching the real and imaginary, first, it doesn't matter. Basically, it will not affect. It will basically result in a rotation, but it will not affect the quality of the image. Okay. So let's go back to the code. How about the real? Basically, what comes out from the transformation is basically an image that looks like this. Basically, these are numbers. K space itself looks like this, but actually it has real and imaginary numbers here. Imagine that we have only one of these. If I have only real numbers or imaginary numbers, okay? In order to test that, what I'm going to do is, maybe I can repeat it so that you can A little bit different code now after it's not going to be exactly the same code as the sample code that I gave you, but you should be able to basically know how it looks like. I actually don't need that here. Don't need that part. That part. Okay, this part here. Okay, sorry, there's a part that I needed. It's this part here. Okay. Basically, in this one here, what I'm going to do is I'm just gonna multiply this imaginary part by 0. Now, the image has only the real part, the first column. Here, I'm going to multiply the first one here by 0. So now the data, the case space is only the second column. So I'm going to try to see now, if I take only the first column, the real part, okay, or the second column alone, okay, what would I come up with? Okay, what I'm trying to say that I'm going to try to show you the importance of both the real and imaginary. Okay, they are both important. You cannot reconstruct without both. Okay, so now if I do that, basically, yes, that's fine. Okay, how do you like that? This is basically, this is the one that we got from the just switching the real and imaginary parts. Here, this is coming from the first real part only. This is from the imaginary part only. Are these acceptable? Yes, go ahead. Yes.
I think both of them the real or not, because all of them without J.
It doesn't matter. Actually, if you have J, it doesn't matter. Maybe you can just put J here. If you want me to put the other way around, okay, I'll just multiply the real part by 0 instead of the imaginary part by 0. It'll be fine. It'll be exactly the same. It's basically, here it came out like something that I'm not sure what it is. Actually, it's nothing, almost nothing. But actually, it's very confusing. Actually, it's very difficult to see the difference between the two. Basically, both are not acceptable. Neither this or that. Imaginary is just basically a rotation. Basically, if you try to reconstruct, the J will be just like a constant. Okay, if you have a constant, then it's not going to affect anything. Basically, if you have J, if you take J as a common factor, then the image will come exactly the same with this factor. Okay, if you take the absolute value here, in order for you to basically display the image, J will disappear. So it's exactly the same. So basically, go ahead.
I think I said it.
I'm not sure I understand what you said.
Okay, I said I think.
Okay. So basically, this is not acceptable. Here, some people may say that this looks like a better image than this one. Actually, it doesn't matter. This is not an acceptable image. Basically, for this particular image, maybe the outline of the skull came out a little bit better than this one here, and the intensity inside might look a little bit better, but actually, this image is full of artifacts. It's not just a matter of the intensity. Actually, if you compare it to this one here, you will see that the image here it has a different texture. So basically, you can have aliases here, you can have different things here that are not present, that are not real. See here how this looks like. See now how this looks like. It looks different. So it's not just a matter of intensity. Both are unacceptable. Both are not realistic images. You cannot accept either of them. Okay, so so the second experiment that we did, maybe you can just write these down. The first experiment, switch real and imaginary data. the output, okay, just rotate. The second experiment, use only real or imaginary data. The output, unacceptable. Okay, what else should we do? In some cases, one of the properties of the Fourier transformation is that if you have shifts in one domain, it will go and basically look like phase in the other domain. Okay, so it means that if I have I'm taking an image of a subject, and this subject moved. Okay, it moved like this. Okay, then the difference between the frequency domain of this one and that one will be just a phase. So it means that in the frequency domain, the absolute value, or maybe I write it as magnitude, the same. It doesn't change. So the shift inside the MRI while you acquire your data is just like when you're taking an image and you have motion. Did you take an image just for, when you're doing photography, if the subject moves and basically sometimes you get a blurred image because of the motion. If you're taking an image of something that is moving very quickly, very fast, you usually get a blur. Okay, it's not a good thing to have a blur. You would like to see the actual object. So would it be possible to take the magnitude, because since the magnitude is okay, magnitude doesn't change, would it be possible to take the magnitude? This is the second experiment, the third experiment that we're going to do now. Experiment, magnitude only reconstruction. So what I'm going to do now, I have real part and imaginary part. What I'm going to do is compute the magnitude and use that to do the reconstruction. Okay, my goal here is to see whether the magnitude, since it's coming from both the real and imaginary parts, would it be sufficient? If it is sufficient, then I don't have any motion problems at all, basically. If the subject moves, then I have no problem because the magnitude doesn't get affected at all. Let's try to do that. How do we do that? Just take this instead of just having this data here. Maybe I can, it's right there, it's already right there. Just shift that a little bit. And since we have figure 3 above, I'm going to have that. Basically, what I'm going to do is basically take the absolute value of the k-space. When I do that, the absolute value will take each one of the points inside the k-space and compute the absolute value, which is the magnitude, and then do the basically the Fourier transformation exactly the same way and display it. Let's see what comes out of that. Wow, that's a very nice image, right? Very useful. This is the reconstruction using the magnitude data. It has nothing, basically. You cannot use it at all. You don't even know what it is. You cannot even guess. So basically, if you try to use the magnitude only, you'll never be able to get anywhere. You're not going to be able to even guess what the image looks like. How about the phase then? Because basically the real part and the imaginary part, basically if you remember the Euler identity, you have x plus j I y is equal to basically magnitude e to the j phase. Each real number or each complex number, basically you can put it, So basically in this result here, let's just put this result here. Very bad, okay? Okay, the Euler identity, you remember from the complex numbers, tells you that x plus jy basically has another phase m e to the j phi. Okay, so you have magnitude and phase, or real and imaginary. These are the two forms of any complex number. Okay, what I'm going to do now is just look at the phase. Let's try to reconstruct only with the phase data. Okay, how to reconstruct from the phase data? We just make the magnitude here equal to 1 so that we can basically remove it from the equation. Okay, if we try to do that, basically it come out like this. So basic experiment number 4, we can just write it as an experiment. Phase only data. Okay, so basically I'm going to take the assume that magnitude is 1 for all points in k space. Okay, in order for us to do that, maybe let's just take this part from here. Maybe I can do it this way, or I can do it in a simpler way. Give me another way so that you learn another way to do that. I'm going to leave that same code because it's in the original data, the code that I gave you before. Basically, I can just compute the angle. The angle of the k space will be basically phi. But I cannot have phi, just phi. I cannot reconstruct from phi here. Phi is above. It's basically the part where the k space has the phi is e to the j phi. So I compute phi from angle using the function angle, and then take exponent of j phi. Okay. Another way to do that is just take the k space and divide it by the magnitude. So basically, I will take the part here where I computed the magnitude, okay, and basically, instead of doing this complicated matter, okay, I hope I didn't miss. I'm just going to have k space dot divide. Basically, I'm going to have element-wise division here. Is there any problem with that? You see any problems in that? Absolutely, can it be 0? I'm not really sure. Sometimes it can actually be 0. And this can be a problem. But actually, in this case, we will have not a number. Let's try it like this. When I do it like this, basically the k space will be divided by its magnitude. So the magnitude will be basically just 1. And so basically the outcome will depend on how the phase looks like. Let's try that. Do you see anything? There's nothing here actually. It's almost not, but actually it might be due to some errors actually. Let me try something a little bit just to make sure that things are not. When you have something that is not that is basically in the denominator, sometimes it's better to just put something very small here. It is basically that's making sure that the number in the denominator is never 0. Because if it's 0, then things will come out a little bit off. Actually, this is the case. Actually, this is basically we got something that looks like something. This is actually, remember what we got before, it looked all black. Now we have something that looks like the outline of the head. So actually the phase is very important. It's even more important than the magnitude sometimes. So basically because of that, we see something. It's not an acceptable image, but it's actually, it's a less distorted version from the one that we computed from this one here. So basically, what comes out here will not be good, but actually will only be just 1x. Okay, it's bad, but it's actually better than this one. This is really bad. Okay, so reconstructing from the phase-only data is not sufficient. So basically, the point that I would like to to make across here is that in order for you to be able to do Fourier transformation, you have to have both the magnitude and the phase. Without both, you're lost. Some people actually think that if we take the Fourier transformation, if you compute the Fourier transformation, you can just keep the magnitude and throw away the phase. If you throw away the phase, you'll never be able to go back. Okay? Because basically, without the phase, you're lost. You cannot compose, we cannot basically put together the signal using the Fourier transformation again. So you cannot ignore the real or the imaginary or the magnitude of the phase. You have to have complete complex numbers. Okay, you have to have magnitude and phase, or real and imaginary numbers put together the right way. Otherwise, you're not going to be able to proceed or do anything with your case space. Okay, is that clear?
Yes, Doctor.
Okay. Okay. Let's move along, and basically what we're going to do is basically this part C here is related to the quantization. This quantization actually is exactly the same as the quantization we did already, but let's do it here also. Okay. So basically, it depends on the number of bits that you have here, that you choose here. I'm just going to display the image. Using the quantization that I selected. Maybe I can just have here image 1, so that, or maybe I can just put image. Okay, it doesn't matter. By choosing the number of bits here, we're going to see the effect of the quantization here. This is exactly the same as what we did before, but let's do it again here so that it's actually part of the code. Let's try with 8 bits first. There's something wrong here. Image 1 is distorted. Oh, okay, because here we actually we distorted that here actually. So that's we did some distortion for image 1, image 2, and then we didn't keep the original. Yes, I'm going to have image equals to image 1 here. But I keep a version that is correct and remove it from there. Quantization. Okay. So this is the original image. Do you see any problems with this image? Looks okay, right? So basically, this is quantized with 8 bits. Does it look okay? Looks okay. If you look at the original one, it's almost the same. It's not much difference, right? Okay, let's start with something that looks bad first, because sometimes it's difficult to know the quality. Let's just put number of bits equal to 2. How about that? This is quantization. Each one of the points in the image is quantized to 2 bits. So you have only 4 colors. Is that okay? Does it look okay, right? So we need more quantization than that. So how about if we choose 3? Acceptable? They're not acceptable. The color variations here are extremely poor. Try 4. A little bit better, but actually we can see the color variations here. They are really poor. They are not really very good. So 4 is still not acceptable. Basically, for this part, as we did before, you have to try it yourself and basically look for the image that you are interested in. So for 5, it looks kind of okay, but if you compare it to the original one here, you will find that it's not that okay. Basically, you don't really see any variations here. You see here in this one here, you can actually see the pixels. You can see the variations between the pixels. If you have a very limited number of colors, then you don't really see the gradients that well. In order for you to see a gradient, a very smooth gradient without pixelation, you have to have really a large number of bits or not large number of colors, so that you can have a very smooth grayscale variation inside them. So this is still not very good, still very poor. Actually, it might not look very good here. You have to actually look at it on your computer so that you can determine that for yourself. So I'm just gonna try 6. A little bit better, but yeah, sometimes some people may say that this is okay, but this is actually not very good. Still, you have to have a little bit larger number. So basically, the conclusion here from this quantization experiment is exactly like what we said before. For quantization, it depends on the kind of image that you have, and basically you have to look at the quality yourself. You cannot say that a number of quantization levels of 6 bits or 8 bits or whatever is sufficient. No, you have to actually experiment with that for each type of images on its own. Okay, you cannot just generalize on that. Okay. Okay. The remaining part is yes. Go ahead.
If we raise the number of bits more than 8, what's happened?
It's fine, because basically what you're coming up, basically the image here is real numbers. When you display it, you scale the images, you scale the colors. Here, because you created the case-based data is real. You look at the image here, it's complex double. Complex double means that you have to actually convert it to integers. You convert it to integers with how many bits, this is what you determine. So you can actually have more than 8 bits, not just 8. The regular images that you see, like the JPEG images or anything like that, it's a little bit different because it's originally coming out or coming in as 8-bit images, like the ones that you saw in the samples in the MATLAB image processing library. Okay, the samples that we use from there. The image itself is already quantized. Here it's not quantized. You actually constructed your image from the k-space, the actual k-space. So it came out as double. You have to determine for yourself the number of bits that you have to use in order for your image to display properly. For such images as the mammography, for example, people are used to 16 bits. Okay, because actually the variations in the mammography are very subtle, so you have to have a very large number of colors so that you can actually detect any small variations. Okay, here you have to determine that for yourself. Okay, so here the image is not like what you saw before. The image here is coming out like double, and actually it's complex because whenever you use Fourier transformation or inverse Fourier transformation, the result will come out as complex. The image here be basically mostly zeros in the imaginary part, but actually basically it's still a complex number. Okay, so you have to take the absolute value. It will come out like double, and then you take the double and basically convert it to integer using the number of quantization bits that you choose. So to answer your question, yes, you can definitely have more than 8 bits. For the other images that you used before, because the image was originally 8 bits, cannot have more. But here you can. And this is the reality. This is the real life. This is what you actually see in real life. The data we are working with actually is real. It's basically an image of a person, and basically the data is exactly what we got from the machine. So basically, it's not like simulated or anything like that. No, this is what you will see in reality. Okay. Okay. So the last part, which is basically the last part of this part of the course of the research problem 1, is basically undersampling. If we do undersampling in the K-space, okay. Basically, I have an undersampling factor here, and basically, like exactly what I told you before, what I do here is I detect the size of the K-space. Let me show it to you here first. The function size, if you have a certain variable inside, it will give you the size of this variable here. Okay, so if I say, for example, x equals to size of K-space, x will be x of 1 will be basically the first dimension, x of 2 will be the second dimension. So what I do here is I have size 1, so that I remember what this is for. Size 1 is the size of K-space. Okay, I try now 2 experiments. Let me just remove that. I try 2 experiments. I try undersampling, basically in the second dimension, and I can try sampling in the first dimension also. Okay. So basically here, if I do this, maybe I can do it also undersampled 1, undersampled 2 here, and the other one is undersampled 1. So basically here I undersample in the first dimension from 1 to size of 1, which is the size of the first one, with a sampling factor, undersampling factor that I put here. The other one here, I do exactly the same, but in the second dimension. Let's reconstruct both images and display them both. Undersampled 1. Okay, now I'm going to have here subplots. Undersampled 1, which is undersampled in the first dimension. This is undersampled in the second dimension. Undersampling meaning that I'm undersampling in this particular dimension, meaning that I'm taking 1 every 2 samples. When I do that in the x direction, the kx, I expect to have aliasing in the x direction. When I do that in the y direction, I expect aliasing in the y direction. Okay, if I do that in both, I expect aliasing in both. Let us try all of them. Okay, I'm going to add another one here. Undersample 3, and I'm going to just copy that. So now I'm undersampling in both directions. I'm going to add another figure here so that you can see all of them. Sorry. This is figure 6. We already have figure 6. Let's make it figure 7. Okay. Let's try that. Now for the first one, we have aliasing in this direction. Here we have aliasing in that direction. Here we have actually both, because actually, see this here? This is like aliasing here, this aliasing here, and this is the aliasing from the other one here. This is the original image. Now what you're seeing is something that looks like this. Let's go here and see what we have here. What we have is something that looks like, let's just imagine that this is our image here. I have something that looks like this. There's another one here because of the periodicity. I have periodic extensions that look like this. Okay, this is the image domain. Okay, so when I have aliasing in this direction here, okay, first of all, we're going to have aliasing in this direction, or X. If I undersample, X, Kx, I expect aliasing X. I undersample in Ky. I expect aliasing Y. When I have both, I'll have aliasing in both. Okay, so now when I have aliasing in X, what's going to happen is that if X is this direction here, what's going to happen is instead of the distance between, this distance here is the sampling rate. If I make it smaller, if I make the sampling smaller, then this distance will be smaller. So basically this will come out like this. This will come out here like this. And basically it's exactly the same here. Okay? The distance between the center of this one and the next is the sampling rate. When you make the sampling rate smaller, then becomes smaller. This becomes smaller until they overlap. So basically the first one came out like this. The second one, this is for this one here. The second one here, this is here, 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 here. Basically the aliasing was in the other direction. Then what's going to happen is that you're going to see something that looks like this. Of course, you have to always remember that what you're looking at is only one period of everything. So if you go back to the figure here, you see that there is a difference. Of course, the X and Y directions, by the way, in the MATLAB are different. So X in MATLAB is in this direction and Y is in this direction. So basically that's why it's like this. So what you're seeing here is the situation here, like this. You have the alias from the one below and the alias from the one above appearing on top of the original one that looks like this. Here, it's very obvious. You have your figure here with the overlaps from the one to the right and the one to the left. Here, it's actually, you see that, you see this, and actually this one is here like this, and this one is here like this. It's not very clear, but they are like this. In order for me to make it a little bit clearer, I think, because actually here the image, as you see here, because I undersampled, the image will come out a little bit, but actually it's okay. It should be okay still. Okay. But basically, when we have aliasing in both directions, you will have something that will basically look like this. Basically, if we have both, we have okay, and basically what is going to happen is that you're going to have aliasing in this direction, and also aliasing in the other direction. So when you look at the image in the middle, you will see that this is the original. You have overlap from here, overlap from here, overlap from here, overlap from here. Because basically the aliases, basically the periodic extensions aliased on the original one. So this is what you have here, the last one. This is actually might not be very clear, but actually if you look at it very clearly, basically you see that first artifact, you see that second artifact right there, and they are both present in the output. So this is very important. People actually, why do people actually have this problem, the aliasing problem? They should actually try to avoid it. But the problem is sometimes you need to acquire the image in less time. Basically, if I have to acquire 1,000 samples, sometimes the acquisition of the data, or usually the acquisition of the data is proportional to the number of samples that you have. Okay? So basically, when you have less points, you have, for example, instead of 1,000, you have 500, you collected the data in half the time. So basically, in theory, you should have the image in less, or basically half the time from the original. Okay. The problem here, when you do that, if this reduction in samples resulted in aliasing, then you lost everything. You have to repeat the image with the correct sample. These images are not acceptable. The one thing that you can do to reduce the imaging time is reduce the number of samples by reducing the bandwidth. Meaning that instead of undersampling, basically, undersampling is not good. Okay, maybe you can use less sampling at correct sampling rate. Meaning that, for example, if I originally collected from here to here, okay, these were like 1,000 samples, okay, and basically this was the rate. I keep doing that, but instead of starting from here, I start from here. Okay, so I take 500 points, but this is exactly the same. This is delta K is exactly the same as this delta K. This means that if I wanted to try that, basically I'll just take my line and basically remove some points and see what comes out when I take only the middle part. Okay, let's try that. This is the last part of this lecture. Okay. So this is the bandwidth, basically, because basically if you remember what we said about the bandwidth, bandwidth was basically this part right there. If I take less points, if I take less, n is less, but delta k is exactly the same, this means that the bandwidth will be a little bit less. Okay, so we're going to try that now. Here, what we do basically I have the bandwidth factor is 2. I'm going to reduce my bandwidth by this number. The way I do it is I just compute the half the size and basically start from the middle and take half the size from this side and that side. So basically, I'll just show it to you here as an algorithm, and then implementation will be very easy for you to understand. If I have 1,000 points, okay, I compute the size will come out as 1,000. Okay, new n dash will be 500. I want to take 500 points from the middle of this array. What should I do? I start from n over 2 minus n dash over 2 to n over 2 plus n dash over 2 minus 1. If you basically compute this range, it will be basically this is the 1,000 points. This new range will be basically 500 points in the middle. Exactly in the middle. The middle of this array is coinciding with this exact array. Let's see what the results look like when we do that. Here it's figure 7. Let's make it figure 8. Okay. Okay, this case space is not there. Maybe I can just use case space 1. Right? Actually, case space should be there. It was already working there. Let me see the error. And okay. So let's move that. Okay. This is what came out. Does it look good? Actually, it doesn't have aliasing. As long as it doesn't have aliasing, then it's acceptable. It's not of very high quality. Definitely an image that looks like the one we saw before. Maybe, yes, this one here. Definitely looks better. But actually, it still looks like an image. Okay, it's a little bit lower resolution. And basically, this is why we actually needed to have more bandwidth, because when you have more bandwidth, you have more resolution on the other side. Because basically, if you go back to the equations, when you reduce the resolution, when you reduce the bandwidth here is related to the TS here, the sampling here, sampling step. So if I reduce the bandwidth here, the pixel will have a larger size, okay? Meaning that basically what you're going to get here is an image with poorer resolution, with half the resolution of the original. It's okay. If you try to, if you have to collect the data in less the time, in half the time, then you have to do it this way. You cannot do it the way. You cannot do it with aliasing. Okay? So the conclusion here is that this image here has lower resolution, but it's acceptable from the point of view that it doesn't have aliasing. Okay? So basically, you're going to stop here. This will be basically the last lecture in the research problem 1. I'm going to basically post an assignment 2, which will have all the remaining parts of assignment 1, of research problem 1. It has a remaining task. I'm going to consider that the parts that were done in assignment 1 as done. We're not going to repeat that in assignment 2. So basically, you consider it as a continuation of assignment 1 to cover all the requirements of research problem 1. So it's going to be basically list of things to do, and it's going to be a little bit maybe compared to the one you did in research problem or assignment 1. It will be actually, it will take less time because the things that we covered after assignment 1 were less. But I'm going to ask you for a report, write a report about these results. So hopefully it's not going to be that that big of a problem. I do not have expectations regarding the report. We have a certain format. Just document what you have the way you like it. That's it. Okay. So inshallah, I will post that inshallah by Friday, hopefully before then. And please feel free to let me know if you have any questions. Starting from next time, inshallah, we're going to have, I'm going to give you at least 2 weeks to finish this part. So we're not going to start with any experiments or any MATLAB coding. The new topic. Next time, I'm going to introduce you to the new topic, which is going to be computer-aided diagnosis. I'm going to focus on some of the theoretical aspects of the computer-aided diagnosis, and basically we're going to try something that we didn't try before, which is using deep learning. Okay, so next time it's just going to be a lecture. We're not going to do any MATLAB coding to give you the chance to finish the coding for research problem. Okay. If you have any questions, please feel free to let me know, or just send me an email or WhatsApp or whatever, and I'll be happy to answer your questions. Do you have any questions for now? Okay. Then this is it for today, inshallah. I'll see you inshallah next Wednesday at the same time at 4:30 inshallah. Thank you very much. Assalamu alaikum.
Alaikum assalam wa rahmatullah. Thanks.